All right, for part two, oops. For part two, we'll pick up where we left off, and we're about to do an example about the decomposition of ammonia. And the equilibrium constant in terms of pressures here was 1.47 times 10 to the minus 6 at 25 degrees Celsius. And let's see, the concentration, the initial concentration of the ammonia is 1.20 atmospheres. We're using, or rather, we're using partial pressures here. And the ammonia, the reaction is 2 ammonias will dissociate into nitrogen and 3 hydrogens. Okay, so we start out with 1.20 atmospheres of ammonia, and we start out and we end up, or sorry, start out with no products at all, 0 and 0. During the course of the reaction, since we have no products at all, it's obvious the reaction is going to be running left to right. And we're going to be losing NH3 and gaining nitrogen and hydrogen. According to the stoichiometry of the reaction, the change in NH3 will be minus 2x. And then for the N2, it'll be plus 1x. And for the hydrogen, it will be plus 3x. So the equilibrium concentration for the ammonia will be 1.20 minus 2x. And for the nitrogen, it's just x. And for the hydrogen, it's just 3x. So when we put those numbers together, and try to come up with the equilibrium constant expression, we know that the number for the equilibrium constant is 1.47 times 10 to the minus 6. And we know that the equilibrium constant is going to be products over reactants. So that's N2 concentration, or actually I'm using brackets here, even though it's partial pressure. That's okay. Actually, I don't mind if you want to do that. As long as you realize that these are pressures and you put the right numbers in the right places, that's okay. But anyway, partial pressure of N2 times partial pressure of H2 to the 3rd power, because the coefficient in the equation is 3, over the partial pressure of NH3 squared. So the equilibrium concentration of ammonia is X. So that's just, or sorry, of nitrogen is X. So that's just X. The equilibrium concentration of hydrogen is 3X. And that has to be raised to the 3rd power, like this one did. And in the denominator, we have 1.20 minus 2x, which has to be squared. Okay, now, I don't know about you, but I really don't look forward to working that problem out. So let's make some assumptions, shall we? This calculation would be really difficult the way it is, but again, if you do what I said and take the initial concentration and find the ratio between that and the equilibrium constant, you find out that the ratio is 816,327. So yeah, that's bigger than 1,000. And so we can definitely make that assumption, which means we can drop the 2x in the 1.20 minus 2x. Okay, then this becomes the equilibrium constant, which is 1.47 times 10 to the minus 6, is equal to x times 3x to the 3rd over 1.20. Oops, squared. Okay, and